So in the last video, what we did was we looked at Cayley's formula, which says that there are n to the power of n minus 2 labeled trees of order n, and we said, okay, well, the proof idea is to get a one-to-one correspondence between labeled trees and these Prufer sequences, which use any of n elements and have length n minus 2. And just as a brief recap, we saw already that these sequences should definitely have length n minus 2, and we did an example where we got from a tree to a Prufer sequence. So I'll just scroll right down to the bottom, and we'll take a look at the sequence that we ended up with. So this was our tree, which it's kind of hard to see anymore because all of the edges are sort of written on top of. But this was the Prufer sequence we ended up with, 1, 7, 6, 6, 1. So now in this video, what I want to do is just to explain how to get from a Prufer sequence to a labeled tree. So we're going to do this direction now, from a Prufer sequence S of length n minus 2 using symbols 1 up to n. How do we go from that thing to a labeled tree? Okay, so first of all, what I'm going to do is similar to last video. I'm going to just sort of give you a step-by-step way to do this and then try the example. So the step-by-step way to do this is going to, first of all, assume that we have a Prufer sequence. So let S be some sequence A1, A2, up to AN minus 2. And remember that each of these AIs belongs to the set 1 up until n. In fact, if your sequence doesn't look exactly like this, then the first thing to do is to shift everything so that it would look like this. So we want to be able to take a Prufer sequence, which has length n minus 2, and it uses symbols 1 to n. Now, not every symbol might be here. Remember that our last example, we got a Prufer sequence which was 1, 7, 6, 6, 1. And that, for example, didn't involve the symbol 2, but it did involve the symbol 6 twice. So that's possible. Okay, so this is our sequence, and here is what we do. We follow this little step-by-step algorithm, which is to find the smallest element, x, which is in the set 1 to n, but that's not in S, where x is not in the Prufer sequence. Okay, so that's step 1. And then what you want to do is to just join this x, so make a vertex with label x to the first element of S. So really that means that you're going to have something like this, x being joined to whatever is the first element. In this case, it's A1, I've called it. Okay, so now what you have to do is delete your A1 from S. You've already used it up. And delete the x from the set, 1 up until n. So for convenience, what I'm going to do is actually call this set right here, 1 up until n, L. So we're talking about x in L, and now what you're going to do is delete x from L. And what I want to do is in the next step, consider the new L, which is the same as L but doesn't have x in it. And similarly, S is the same sequence, but it doesn't have A1 in it. So now we repeat the same sort of idea. We want to find the smallest element. I'll call this one Y. It's still in L. Well, maybe I should be more clear. It's in L without x, right? And it's also not in the sequence. And again, this sequence doesn't have A1 anymore. Okay, what we're going to do is the sort of same process. We're going to join Y to the first element of S. And again, this S doesn't have A1. Maybe just again to be super clear, this is S without A1. So this is S without A1. And the first element of that is, of course, A2. So what you're going to be doing is joining Y up to A2. And then again, we delete our A2 from S, and we also delete our Y from L. So now L is reduced a lot. L no longer has the value X and no longer has the value Y. And you just continue this process. So I've only sort of written 2 of the steps, but you see that each of those steps is the same. So you just continue this process, continue until 2 items remain in L. And then what you do with these 2 items is you join these 2 via an edge. Okay, and I claim to you that this thing that you've built with all these little edges is actually the tree, the labeled tree that you're wanting to get. So let's do an example. My example, not surprisingly, is going to be 1, 7, 6, 6, 1. And the reason I've chosen that example is kind of obvious, because I'm hoping to show you that we get back the tree we started with in the last video. So first thing to notice is that this has length 5. 1, 2, 3, 4, 5. So length 5. Well, that means that our n must be 7. And it's nice, we have value 1 through 7 clearly represented here. Now, it may not be the case that 7 is here. It could have been a 1, 5, 6, 6, 1. That's fine. But we still know that n is 7 just based on the length of the sequence. Okay, so let's set ourselves up. We know that L is just 1 through n. So 1, 2, 3, all the way up to 7. Okay, step number 1 said find the smallest element which is in L that does not belong to S. So you think, okay, maybe the smallest element in L is 1, but that does belong to S. So the first thing that's in L that doesn't belong to S is this 2 right here. So at the moment, we're looking for X, which is in L, but is not in S, and that is smallest. So we're getting X equals 2. Okay, and what we have to do is join this to the first element in the sequence. So we say, okay, I'm going to join a 1 and a 2. And that's it. That's all I know right now. Now I have to delete the 2 from L, and I have to delete the 1 from S. So I move on. Maybe I'll just write down what we have now. We now have S is equal to 7, 6, 6, 1. Our new L is really equal to 1, not the 2, 3, 4, 5, 6, 7. Okay? Now, step number 2. We look again for the smallest thing in L, which does not belong to S, and that's a 3. And we join this 3 to the next thing that's in S. So we've already deleted the first thing, so it's the next thing. So that means we're going to add a 7 and a 3 with an edge. So now we delete this 3 and this 7. And now we repeat. We look for the smallest thing that's in L, which is not in S. And we see that 4 is the smallest, not in S. So we join the 4 and we join the 6. There isn't a 4 and there isn't a 6 yet, so we just create them, 4 and 6, and join them by an edge. And then we look again through here and we say, okay, what is it that is the smallest thing in L that's not in S? And we get the 5. And so we join the 5 to the 6. And 6 is already here as a vertex, so simply join the 5 to the 6 like that and delete them. Now we still have 3 things left in L. And the smallest thing in L that's not in S is this 6 right here. So we will go ahead and take the 6 and this 1 and join up 6 and 1. Okay, well 6 is already here and so is 1, so we just join those up by an edge and then we delete them both. And now what do we have? Well, we only have 2 things left in L. They are 1 and 7. And our rule tells us that when we get to this point where we have only 2 items left in L, we should just go ahead and join those via an edge. So we join 1 and 7. 1 and 7 like that. Okay, In fact, this is exactly the tree. This right here is exactly the tree that we started with in the other video. I believe I just happened to draw it slightly different in space, but the same labels and relationships are all there. If I just redraw this again for you, you'll see what I mean. So all I'm going to do is I'm going to put the 2 over on that side and the 1 here. And now I'm going to draw the 7 above the 1 and then the 3 above that. And what else is adjacent to the 1? Well, 1 is also adjacent to this 6, and that's also adjacent to a 4 and a 5. So you'll notice that this is the way that I drew the tree in the last video. This is, of course, the same exact tree. So what we were able to do was we were able to easily go from our Prufer sequence S to our tree T. And, of course, we are able to go from our tree T to our Prufer sequence S. So we basically have a description for how to go between a labeled tree and a Prufer sequence. And the proof is not complete. This is just an example. You would have to rigorously show that this is a one-to-one correspondence in order to complete the proof. But I hope that the idea really helps you understand why it is that there are n to the power of n minus 2 labeled trees of order n. See you next time.